Ah. Wow. Wow. Oh, wow. Oh. Okay. 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 I see. Bunch of trolls in the chat today. Oh, nice. Yeah. Nice. Glasses. Allison. It's... And the teeth. The teeth are accurate. That's awesome. Let's see. Will my class show up? Not today. Oh. Second, gotta make sure I know what I'm teaching today. 1 second. Check these. Yes, yes, yes. Good. I believe it's a little bit of both, Sandstrom. But it's, yeah. These lectures become the lectures of the class. That's right. Oh, Gath is here. Wow, Gath. Gath is a great organic chemistry teacher. And I need to shout out Gath. Check out Gath, folks. Her classes are so perfectly designed. And they have like games and stuff that are educational. Yeah. Inspiring. It doesn't, you don't need to know that stuff, Sandstrom. You know? Just, you know, stay in your lane, you know? Yeah. Yeah, I guess it is random nerds today. Yeah. Oh, Sandstrom, the class is elementary algebra. Like what you learn in 3rd grade? Oh, it's alright, Gath. You are welcome to come in and out whenever. Oh, wow. All day? Okay, never mind, folks. Don't enroll in one of Gath's classes. They have week-long tests. So don't go and enroll in Gath's class. That sounds like a... Oh, okay, that makes more sense. Okay. Oh, the level is elementary algebra, my dear Sandstrom. Okay, let's let's start. Let's start. Oh my god, I better close that door, otherwise people will figure out where I live. All right. So, next thing. Where is our music? Okay. Play this. All right. Here we go. We return to our elementary algebra class. And we're in the middle of the topic, very important topic, of group actions. A group can act on a set. All right, so that's the fact of life that we're understanding. Fact of life. A group can act in different creative ways. You come up with actions. I can't list all the actions in this world. In all mathematicians' lives, careers, you can't predict when you're gonna encounter a group acting on a particular set. It's just so commonly occurring. So a group G can act on all sorts of sets. And it's very important to distinguish the set that it's acting on from it itself. These are apples and oranges. And those who identify a group with one of its actions, those people will not appreciate how the same group can manifest in multiple different ways. They're wedded to one interpretation of this group. Then when it shows up again, they won't be prepared. They won't be prepared. They'll be perpetually confused. Like, wait, but this group was only this. No, the group is only itself. The different sets it acts on are different sets that it acts on. The different actions, the different ways it acts are different ways of acting. But the group is itself, and the different ways of acting are those other things. Important to keep things straight. So now, the first thing I'm going to talk about now are very important group actions. Okay, so I'm going to talk about that. I'm going to focus on one particular one. Conjugation. So here's how it goes. I'm going to define what conjugation means. So suppose G is a group. And little g, of course, is an element. And then little a is an element too. Then you can conjugate A by G. And what that means is this group multiplication. G times A times G inverse on the other side. All right? Okay. So this produces another element in the group, of course. All right? So this is also an element in G. Okay. So this will be a tongue twister. All right? The tongue twister is the following. Conjugation is an action of G on the set G itself. In other words, so i.e., the map which sends G to conjugate by G, which you can write like this. This little symbol means a little function from G to itself called conjugate by G. Like Gx G inverse. Like X goes to Gx G inverse under this map. Conjugation by G is a function from the group to itself. And so if you assign to each element of the group conjugation by it, this assignment actually is a group action. So what we have to check that conjugation by G times H is conjugation by G composed with conjugation by H. That's what we need to check in order for conjugation by blank to be a group action of the group on itself. Okay, so let's check this. Okay. GH applied to an element, GH inverse, that's conjugation, that's what conjugation by GH will do to an element X. This is what conjugation by GH does to an element X. All right, but now if you do this carefully, now you do some math, algebra, just do some algebra. I mean, we are in an algebra class, so we should probably write algebra every now and then. Convince ourselves that that's what's happening. Get Gx H inverse G inverse, the shoes and socks or whatever it's called. Okay, but notice what this is. This is G all right, and now I'm gonna twist my tongue to say what that last part is. But this is exactly conjugate by G the following thing, conjugate by H. The element X. Okay, so therefore conjugation by the product G times H is the same as conjugate by G composed conjugate by H. So the act of conjugation is a particular way in which the group acts on itself. All right? So conjugation. Oh, why didn't I give a name? Conjugation is the name of this action. The word is conjugation. Okay? Oh, video game cheating? Yeah, I do. You're gonna get ignored because I'm teaching class right now. All right. So conjugation is the name of this action. The group acts on itself in this way. The group acts on itself in other ways too. The group acts on itself in other ways too. For example, left translation. Namely, to each element in the group G, assign the scrambling of the group called multiplication on the left by G. permutation left multiply by G. Multiplication by an element on the left induces a permutation of the group G. Go and check that this is an action. This produces an action of the group G on the set G. Okay, let me show you another setting where you'll find a group action. Another setting. If you have the setting of H, a subgroup of a group, then G acts on the left cosets. I'm going to start giving giving notation for the set of left cosets. It's written like this. Okay? It's just notation. It's just a set of all left cosets of the group G, of the subgroup H in G, okay? Don't look into it anymore. It's a set. It's just a set, folks. If H is a subgroup, then G acts on the set of left cosets by left multiplication again. In other words, an element in the group is sent to the permutation of the cosets, the permutation of GH, which is like this. A coset gets sent to this coset. So the group shifts the left cosets, scrambles the left cosets around via left multiplication. The group scrambles itself around via left multiplication. But the group also scrambles itself around via conjugation. And there's a very important distinction. There's a very important reason why conjugation is more interesting and special and delicate than, say, left translation action of the group on itself. So let's look at a curious property of translation, of conjugation. Conjugation is interesting. Because conjugation by an element is not a random permutation of the group. Conjugation by an element is not a random permutation of the group G, of the elements of the group. It's actually an isomorphism from the group to itself. An isomorphism, not just a random bijection. It's not a random not a random bijection from G to itself. It's an isomorphism. Of the group G to itself. Let's check that. What we're saying is that the conjugation of a product is the product of the conjugations. Look at this. This is just algebra, folks. Okay? And that's not the case with the action of left translation. Conjugation is a particular kind of bijection of a group with itself. It's an isomorphism of the group into itself. All right, so there's a word for that kind of a thing. An isomorphism of a group to itself is called an automorphism. So the group of and isomorphisms composed to be isomorphisms, etc. So the automorphisms of a group form a subgroup of the set of all permutations of the group. Permutations are just random scramblings of the elements. Automorphisms are not random, they're delicate. They preserve the group structure. They are bijections which keep the group structure in alignment somehow. They preserve, well, they're isomorphisms. You know the definition of an isomorphism between the group and itself. All right, so inside the group of all permutations, you have the group of automorphisms of G. All right, so you have the subgroup. How to think about this? The way you want to think about this is the symmetries of the group G. And this is like the symmetries of the set. It's easy to just create a symmetry of a set, that's just a permutation. But to create a symmetry of the group, including its group structure, that's much more delicate. And conjugation is an enormous class, an enormous collection of automorphisms of a given group, G. So that's why conjugation plays a very important role in group theory. It's not just that the conjugation permutes the elements of the group, it preserves the group structure. Conjugation lives in automorphisms of the group G rather than just an ordinary old permutation. All right? And the last thing I want to say about conjugation is that you have seen conjugation before. You have studied one particular case of conjugation thoroughly. You have maybe studied one particular instance of conjugation in one particular group. The group was GLN. N by N invertible matrices. And instead of like G inverse, you probably saw the letters SAS inverse equals B. Something like this. Where S was an invertible matrix, there's something called a change of basis matrix or something specific for that context. And then this two matrices were similar if one was conjugate to if there was an S that made one A become B. All right, this is something called similarity of matrices or something. And then maybe you learn that every matrix is similar to a matrix that has the following shape. I don't know. Some people learn this, some people don't learn this, but Jordan canonical form and stuff like this. Yeah? Whatever. Like, every matrix is similar or conjugate, now we can use that, to a matrix of this form. I'm just maybe jogging some memories, maybe not. Some matrices were special because they were conjugate to a diagonal matrix. That was called a diagonalizable matrix, and so on. What my point is that linear algebra in that chapter was an in-depth study of the action of conjugation in GLN. Okay? But notice, conjugation exists all over the place. And if you were only wedded to conjugation in GLN, you would not realize that it's such an enormous construction, and that there's opportunity for you to study conjugation in all kinds of other groups in this world. That's the power of abstraction, that you distill to the core of what was going on. So conjugation, you already know what conjugation was. In the case of change of basis discussion in linear algebra. Okay? So the less diverse sort of and special looking constructions look in math, the better you're becoming at mathematics. More things are becoming uniform and manifestations of just same underlying principles. So conjugation, if you believe that it was important in linear algebra, that's enough for you to buy in to maybe focusing on it in group theory class. We'll see that it's important later, just in different applications of studying group and conjugation within the group. We'll see it very importantly, maybe second half of next week, starting second half of next week. But I just want to put this in front of you. Conjugation is an automorphism of the group G, and the act of conjugating is a way that the group acts on itself. Okay, great. So now move away. I'm now gonna show you another situation where a group action helps solve a problem. All right. So I haven't shown you I haven't shown you a single instance where a group action actually helps you solve a problem. All right. So what's the point of group actions? All right, let me show you one. You won't be able to deny the power of group action, concept of a group action, and orbit stabilizer after I show you this. So then you can just shut up after this. Okay, so I want to prove a theorem. Let's prove a theorem. Okay, this theorem is humanity's best response to Lagrange's theorem. Okay? The converse of Lagrange's theorem is false. Students, come up with a counterexample in A4, the alternating group A4. There's no subgroup of order 6, even though 6 divides 12. 6 divides the order of A4, but there's no subgroup that has 6 elements. Go and try to play around in A4 and realize that. Okay, but there's one particular flavor of converse statement to Lagrange's theorem that's true. And here's the theorem. And it's an important theorem, very important theorem. If a prime number divides the order of a finite group, I mean, to say that it divides, it's implied we're talking about the finite setting of a finite group G, then there must be an element of order P. And therefore, there must be a little cyclic subgroup of order P in G. So you can guarantee the existence of a prime order cyclic subgroup in any given group G, as long as the prime divides the order of the group. That's the rules after. That's just part of life after Lagrange's theorem. Okay, it's a marvelous theorem. It's impossible if you just sit and try to write the group multiplication table, old school style. Several of you have had great misery in the homework, and that's on purpose. I'm glad that you went and saw how hard it is to just argue using a multiplication table and some Sudoku style logic. It's just way too many cases to check and keep track of. But check out this theorem. Now I'm gonna show you the brilliant, classic, awesome proof of this theorem. Okay, so check out this proof. And really, I know there are some who still resist learning algebra. They scoff at it. But please, put your ego aside and check out this proof. And check out the power of group actions here. Now look at this. So what we're gonna do first is construct a set. Consider the following set. I'm gonna call it A. Actually, let's call it X so that my students don't get confused. X. Because we're gonna act on this somehow. We're gonna act on this set. But what is this set? It's the set of all p tuples of elements in the group which multiply to be the identity. This is one of the most gorgeous proofs in early modern mathematics, right? In your math undergraduate courses. This is going to be one of the most pretty proofs you'll see. So you look at all ways of listing p elements in the group where the product of them becomes the identity. Okay? This is clearly a subset of G cross G p times. Let's consider the following set. Now let's take some vital signs of this set. How many elements does this set have? Step 2. Understand X. Now, how big is X? Right? How big is X? Well, if you try to just dive in and count this, it might be a struggle. But here's the key. Here's the key. If you have p elements that multiply to the identity, then the last element is perfectly frozen once you choose the first p minus 1. The first p minus 1 have to determine the last one, because you have to multiply by the inverse of the product of the first p minus 1. That's what g sub p would have to be. Determines the last entry. That's the first thing to observe. Second, you can put any choices for the first p minus 1 elements, because you can always save the product, swoop in by multiplying by inverse of something to get to identity. So you can freely choose the first p minus 1 entries. So how big is X? It is p minus 1 times the size of the group G. Okay? Alright, so that's how big the group is. I mean the set X. That's our set X, it's a finite set. That's how many elements it has. Alright, step 3, come up with an action. Which group is going to act on this set X? Z mod PZ. There is an action. Of Z mod PZ on the set X.
The name of this action is cyclic shift to the right. Musical chairs. Cyclic shift to the right. Last one goes to the front. All right? So, a tuple gets sent under the element. So, what does 1 do? Here's what 1 does. Shift by 1. It does shift by 1. Okay? That's what it does. What does 2 do? Shift by 2. What does 3 do? Shift by 3. So this is a action. This creates an action of z mod pz on the set X. Shift by 3 and then shift by 4 is the same as shift by 7. There you go. I just verified that the action is actually an action. All right. So, okay. So one thing you have to confirm though, why is this element still in X? That's because if star times square equals identity, then square times star also equals identity. By uniqueness of inverses. All right? And all I'm doing is applying that to G1 up to GP minus 1 times GP equals identity. Then so does GP times G1. And so indeed, this cyclically shifted string is also in the set X. That's good to, that's a relief. All right. So yes, indeed, there is an action of z mod pz on the set X. All right. Step 4. Let's zoom in on this action. Let's look at some really stupid elements in X. A stupid element. E, 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 E. This is an element in X. I hope you understand that. Look at this element. How big is the orbit of that element? Big is the orbit of this element. Orbit of stupid. This is called stupid. How big is the orbit of stupid? Size 1. Answer. 1. The whole group z mod pz fixes this point. So the orbit has size 1 for this element. Okay? So folks, just to summarize, there are singleton orbits of this group action. There is one. It's the stupid one. I just found one. Okay. Next thing we should say is, wait, what does it mean to have an orbit of size 1 in general? Step 5. What does it mean to have an orbit for what does it mean for the string G1 to GP to have an orbit of size 1? Answer. it means G1 has to equal G2, has to equal G3, has to equal G4, has to equal G blah 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 blah. Because the orbit is just what happens when you cyclically shift this string. Answer is they all have to be the same element. And in particular, this element, if you call it just G, this element to the pth power would have to be identity. And if G is not the identity element, which is what you'd get if in the stupid point, if G is not the identity element, there you go. You found an element that has to have order P because it has to have order dividing P, but not have order 1 because it's not the identity. So the hunt for order P elements has now changed to, are there any other orbits that have size 1? So the question becomes, step 6. Are there any orbits, any other orbits, non-stupid, of size 1? That's where we shift our focus. If there is, then we're done. We proved the theorem. Okay, so let's focus on this question. All right, maybe we should understand what are all the possible sizes of orbits. Okay, what are all the possible sizes of orbits? Well, by the orbit stabilizer theorem, the size of an orbit has to divide the size of the group G. Sorry, our group G. The group that's acting, not our group that we started with. Very bad mistake. Okay? This is prime number P. So there are two options. Either an orbit has size 1, or the other option is size P. If not 1, then the size of the orbit equals P. All right, so I'm now going to show you it can't possibly be the case that every non-stupid orbit has size P. If every non-stupid orbit had size P, well, remember folks, the orbits partition the set on which G is acting. Two orbits don't intersect. If they intersect, they're equal. And if they're not equal, they just are disjoint. So we would end up with 1, this is the size of stupid orbit, plus, now collect all the other orbits, which by hypothesis are all size P. P times something. Something being the number of non-stupid orbits. This would have to equal the total number of elements in the set X. But this is P minus 1 times the size of the group. And now you notice that P divides this, and P divides this by hypothesis, and that's impossible because there's a remainder 1 here. All right, and so the proof is done. So there is an element of order P. Okay, so that's the converse. That's basically the strongest converse to Lagrange's theorem that we learned in elementary first stage group theory. All right, and now there should definitely be no one who scoffs at the idea of the utility of a group action. This is the type of argument that group theory sort of starts growing out of. Like clever uses of group actions on objects that are constructed from the group itself. Like this is an instance of that kind of rubric of group theoretical proofs. But you get great mileage out of these definitions. And it's not just some, postmodern, just garbage bubble in academia. This is real. Look at, I just showed you how real it was. Imagine, class, if I asked you to just do this. Like, without learning what an action was or anything. You just have to go and figure it out from case check in a multiplication table. You would all be crying, okay? And I hope you can admit that to yourself. And then, therefore, join me on the appreciation side of abstract algebra rather than on the skeptic side. Okay, so, or linear algebra becomes one example, study of one group, GLN. Okay, awesome. All right, great. So that's the awesome life after orbit stabilizer teaser I wanted to show you. We now know that a group of order 35 definitely has an element of order 5 and definitely has an element of order 7. Now we will keep swinging. We will eventually show that that group has to be abelian. So, how on earth do you do something like that? Well, we're just gonna take this observation and study conjugation a little bit more. And then we'll know that this group of order 35, every group of order 35 is abelian, for example. Just random example. Okay? Can I turn off the music? Yeah. Okay. All right. Okay, so that's the teaser for life after orbit stabilizer. Next week will be like a whole week, or a lot of the week will be using orbit stabilizer to count stuff. So next week is a fun week. Use orbit stabilizer. Or some other thing called Burnside's theorem. But Burnside's theorem is actually due to a famous mathematician named Frobenius. Burnside's theorem, due to Frobenius, will allow us to do counting problems, like count the number of necklaces that are black and white beads. That one problem I showed you on Monday. That one setup. Count the number of necklaces with black white beads or whatever. Count the number of ways to color the corners of a cube. Blah 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 blah. If you do this and this. If you don't learn Burnside's theorem, each one of those problems will feel like a complete random counting problem. But if you learn orbit stabilizer and Burnside's theorem, all of those problems have the same strategy. Easy strategy. Okay, so that's the that's what's coming up next week in where we witness life after orbit stabilizer in other ways, counting problem ways, combinatorics ways. Okay, now finally, in the last 1 minute of class, let's go look at some groups visually. Let's go into the third eye. All right, let's go, just for fun. Let's go check out the tetrahedron group, the group of rotational symmetries of a tetrahedron, and let's just talk about it. I'm going to talk about it in the context of group actions. All right, here we go. Now, do this. All right, let's go check out some group actions, folks. All right, are we here? Yeah, we're here. Okay, let's go. Go ahead on over here, folks, to our abstract algebra world. Oh, hello, Arbitrary. Nice to see you. I can actually talk to people now. because I'm not in class mode anymore. Class, you can leave if you need to. All right. Hello? Boring Professor Servant created this whole universe. This person created this whole world and is continuing to create it just for you guys. Okay? And of course it's merely I mean, technically, you know, all of this is happening in my mind's eye. This is all happening. This is what it feels like to be me, but he has mapped it all out. He's mapped it out into a computer program. Okay? All right. Oh, awesome. Esteemed guests here. Very important guests. Okay. Awesome. All right. Let's go check out the rotational group of symmetries, group of rotational symmetries of a tetrahedron. Okay? All right. Let's go do some rotations here just to get a sense. R1, 1, 2. There we go. Do this thing. Whoa, check that out. Maybe I do it slower. Insane. Rotation around the red dot kind of twice. R11 would be rotating once. All right. RA or RB are different kinds of rotations that keep the tetrahedron fixed. It looks confusing, but if you look at it from the right point of view, I believe if you look at it from here, it'll become convincing. Yeah, that looks convincing. Yeah, so there are these kinds of rotations too. All right, so what I want to point out to you, class, as an excuse to use this software, mainly, is the following. So, the group of symmetries, of the tetrahedron can act, or acts. I mean, it acts. That's the word of the week, folks. Action. The group of symmetries of a tetrahedron acts on various auxiliary sets. Natural sets. X. For example, X could be the set of vertices right? This is a 4-element set. It also acts, X could be the set of edges. Like, how many edges are there? Like 6 or something. 6? Are there 6 edges? Yeah, 6 edges. It could also be the faces. All right, which is also a 4-element set. Okay, but what the thing I want to point out is that sometimes in certain math problems or in certain contexts, you might want to consider the way the group is acting on this auxiliary piece of the object that you started with, or this little part. It's kind of like focusing on the effect of the group acting on these little like pieces of the object. This is another way of creating many examples of group actions from, let's say, one starting group action, namely the action of the tetrahedron group on the tetrahedron itself. Okay, so I just want to point this out to you as a just sort of a phenomenon. Okay. Great. Let's give everyone their due attention. Thanks for showing up to class. Oh, hi Guru. Hi Joe. Hi L. Hi Algebraic the Challenged. Hi Mustard. Hi Kappa. Hi Tropical. Hi Brother. Hi RB Tree. All right, let's get out of here, folks. Okay. Oh, lots of sleeping happening. Great. Okay. So this is actually a very important little observation that might be useful for my class, especially if they are preparing for the exam, where I'm going to ask just tons of questions that simply test whether you understand the definition of a group action. But I'm going to use various examples and fake examples, and it's your task to figure out when are you witnessing an honest group action and when is this thing that you just defined not a group action. Doesn't even make any sense what the heck you just defined. That's the kind of true false that you'll expect in Sunday's fantastic, pleasant weekly exams, which you guys have been doing really good in, so that's good. Okay, let me go check out chat now and see if there was any trolling. I didn't properly note the definition of X, and now I'm a nodder. Kappa, that's the worst. Yeah. Kappa, just watch the YouTube video afterwards. It's beautiful. I guarantee that you will not regret learning that proof. Oh, bored high school junior. Well, welcome. Getting an early start. I mean, this is just algebra, so as what was it? Sandstrom understands, this is just algebra, so no big deal. Oh, Diatom's Attack! Hey, welcome, Diatom's Attack. Hey, everyone check out Diatom's Attack. Conjugation is delicate. That's right. Turn down music a bit? Oh. You mean like over here and not in my volume. I see. My bad. Okay. All right. Kappa, there will be other instances of an action of a group on the group itself in some funny way, or something involving the group itself, which is fruitful to understand. There will be at least one more instance where that happens. So feel free to check that out when that happens and appreciate it when it happens. But yeah, there's and like if you get into if you become an actual group theorist, which is a long road, and I'm not sure it's a very lucrative field at the moment. This is how math seasons go. But if you become an actual group theorist, then you'll see in the group theory literature all sorts of beautiful constructions of groups acting on sets which are produced from playing around with the group itself. There are some crazy trees, graphs that you can create from a group. Kind of infinite, crazy, bizarre-looking graph, fractal-like. And the group acts on it, and then understanding the dynamics of that action can produce results about groups. It's called the Cayley graph, the group. There's all kinds of these brilliant group actions that are born just from a group with insane creativity. And it's just sort of a running theme in the subject. Pointers set theory. No idea what that is. No idea what that is. Oh, hello, Crow. Pointers set theory. I've never heard of that. Let me check that out. I'm so glad that I turned off chat can't share links, because the other day yesterday I successfully rickrolled someone for the first time. It was really cool. But let me go check up pointers set theory. Wait, what is this? Pointers set theory. Oh, this is some computer stuff. A pointer is an object in programming languages. Yeah. I don't know what this has to do with group theory though. Maybe it does. I don't know, but it seems... I don't think it's a very traditional math word. I don't know. Okay. Okay. Oh, Pinter. 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 Okay, what's Pinter? What's Pinter? Let's see. Never heard of that either. Pinters. That's here. I mean, if it's an alternate... Oh, wait, what? This is an author, and they have a book. Oh, it's a book. It's a book. Okay, okay, whatever. All right, so there's all kinds of set theory books out there, and you can learn set theory from anyone who writes a set theory textbook. But we don't really need that much set theory here. We just need to know what a set is and what a product of two sets is, and etc. So. All right. I am definitely. Yeah, I am Crow. I am a mathematician. A mathematician. That's what I am. A mathematician. Bro, you got it. You got it. That's right. Anybody can be a mathematician. Yeah. Oh, you need your shungite? Need your shungite? Tropical? Oh, Pinter is a classic? Oh, okay. I just learned from some random book. There's your shungite, Tropical. Where's my list of events? I usually have a list of events up here. Yeah, anyways, it was really cool when I rickrolled Tayo. That was really cool. Yeah. So, I'm really happy that that happened. Oh, Kappa's lecturing us. Yes, Kappa, preach, Kappa. Go and preach that. Important for people to know this. Preach. Amen. Math is enormous. But what we're learning is standard curriculum. So don't start using that as an excuse. Too early. Don't start using it as a discouragement too early. Delicate balance. wield that phrase with maturity. Yeah, it's enormous, but that doesn't mean you put the pencil down right away. No, we're at the Burnside. The person group theory became completely formalized and looked the way it is now around 1900s. Okay, so I'm just BSing some history now. Okay, so but you know, I think a person majoring in math or getting a master's in math should be comfortable with what happened in the 1900s. Oh, boring history professor. Yeah. Oh, yeah. I shouldn't get started. And it's all wrong. My history is always wrong. Like, I've told the history of like the evolution of the concept of number, like, just completely wrong, and the students don't know. So, but it's, you know, sometimes you just have to tell a story, and they get hooked in. Yeah, I've just BS so many history stories. That's right, Kappa. That's right. Yeah. So Kappa, the ideas were in the minds of basically every mathematician, as Crow would say. However, no one had written down any kind of coherent theory with G's. Like G's and H's. No one had written anything. No one had distilled that this is a part of mathematics. It's just they knew it when they saw it. They knew the principles when they saw it. And yeah, Galois did not know Lagrange's theorem as stated in a textbook. He didn't learn it anywhere. He didn't see it. He didn't know even to write a capital G. You won't find capital G in Galois' diary or anything. He'll talk about the transformations of the roots that keep a polynomial the same or whatever, or keep a field the same. But it was all just in their brains and wasn't codified. That's the word. Until 1900. About. Burnside is the first person who sat down and wrote about group theory for its own sake. That there's a thing called a group. And the group can act on other things, etc. Yeah, he didn't write his own name. Yeah, he didn't write capital G. Like, he only used lowercase g when he wrote his own name. You're right, Kappa. That's right. That's right. Yeah, Galois theory is next semester, Kappa. So if you're still around, which, I mean, you will be, I hope. That went dark. But next semester is Galois theory for this class. Well, yeah, that was algebraically challenged. That was a bad, like, it just, I meant around here, like watching the stream. Like watching the stream. Like, oh my god. Okay, I'm just gonna stop. But yeah, Kappa, seriously, next semester is Galois theory. I'm trying to teach online, but maybe the university will watch this and say, wait a second. Did you notice who's in chat? People like Kappa and Crow and Tropical and Sandstrom. We can't have our students exposed to such weirdos. Mustard Walrus. They might notice this, and then they'll shut the whole operation down. So, well, but hopefully I do get to teach online again. Algebraically challenged. I didn't want to lump you in with the degenerates. Yeah, yeah. I don't think you are of the same stratum of society that Crow and Tropical and Kappa and Guru, these people are just the bottom of the barrel, folks. And if the university finds out that these people are in the chat, it's just GG, you know? Alright. Teacher's pet. Who's teacher's pet? Oh, I gotta say thank you to people. No one's teacher's pet. Okay. Thank you, Chance. Thank you, Perler Dude. Thank you. Okay, these are all. 20 minutes ago they left. They're not gonna get their self-esteem boost. In exit asks, Mustard. Oh, Shanghai. Yeah, here. Digi. The Suber. Professor Laser. All right. How rude. I'm a good person who wants to learn. Degenerates? A bit rash, no? Oh wait, yeah, also I forgot to lump Space-Time Explorer in with that group. Yeah, I mean, it's just... I mean, the university can't know that this is what goes on. Yeah. Oh, and who is... Chat, who is the king of all degenerates in the chat? Who is that? Chat. It's the person who just showed up. It's Dr. Young's lab. Close second, Professor Melko, Crow. I see what you're thinking. Yeah, I agree with you. They're close. It's neck and neck. Okay. And Dr. Young's lab redeems teacher's pet. It's like the worst. It's like I don't want that teacher's pet. I don't want that. Every time this happens. Yeah, Kappa, you're gonna have to start working on that now. Kappa, start working on that hole now. Let your shovel act on the dirt. Let your shovel act on the dirt. Kappa. Alright, I'm the greatest mathematician of all time. Yes, you are, Dr. Young's lab, because you're a teacher's pet, and everything you say is good and right. Good job. Good job, Dr. Young's lab. You know what? Dr. Young's lab, you get a sticker for that. I paid money to get these stickers. So you know what, Dr. Young's lab? I'm gonna give you a sticker for being teacher's pet. Stickers. Here you go. Here's a little sticker for you, Dr. Young's lab. Yeah, let's not talk about perks of the channel because not much. Get stickers. Yeah, this is the perk. If you subscribe, then I will show you a sticker that I paid for. And it'll be addressed to you. Here, I'll sign it. This is what you get for subscribing. All right. Oh, students can never subscribe. Okay, here you go. Here's your signed copy. There you go. Dr. Young's lab. Take a photo of that. Sell it. Make a couple dollars. All right. Okay. So, let's go. Let's get out of here. Sell it on eBay. Pandemic watch. Pandemic watch. Wow. Welcome. Jake, welcome. 1000101. New person. Yeah, new person. Hey. Fellow degenerate. We're doing good. We're just hanging out. Fate? No, that's... Yeah, it's fate. Yes, bro, it's fate. Okay, it's fate.
Wow, Dr. Young's lab. Wow.
Hey, Dr. Young's lab. Do you have links enabled on your chat? Like, do you let your chat like share links on your channel? I'm just asking, like, for a friend. I'm just seeing like who enables links and who doesn't, you know? And when will you be live next? Here, I'll trade. Here, I'll even shout you out. Just answer my question, okay? Do you have links enabled? You do. Good to know. All right. And when will you be live next? Just for my viewers. Don't you want to advertise your stream? Like, when are you going to be live next? Awesome opportunity. You got 20 folks here. Tuesday. All right, Tuesday. Let me write that down real fast. Tuesday, 4:30 p.m. Eastern. Awesome. Folks, go check out go check out Dr. Young's lab. Yeah, I missed the Rocket Sage thing. I missed it. I went in and it was over by the time I went. I wanted to see that. That everyone check that out too. Go back in time and go check that out and follow Dr. Young's lab so you'll know when they'll be online next. And Rocket Sage. Oh, hi, Fox Fruitcake. I assume you're talking about me. Not Dr. Young's lab's class. But Dr. Young's lab's class is also really cool. Very awesome, actually. Incredible. That time is called Eastern. Yeah, you can watch the VOD. It was fun. Awesome. Yeah. Yeah, no, I saw some of it. Like, you guys were looking at some weird crystals. Like, I mean, it wasn't as cool as this, but it was close to this level of, like, coolness. You know? You guys were looking at some weird rocks. Really cool. That's a different channel, Admiral Stapler. That's different. You gotta go to UB Math Prof for that. If you want to see an exciting math prof, you gotta go check out UB Math Prof. Okay, they're not here, obviously, because they're losers, but check out UB Math Prof at some point. Right? Check out Professor Peter. If you want actual professors. Oh, well, UB Math Prof's a professor too, but if you want professors, you know, you want to have high quality education, check out Professor Peter. Did I get this right? I did. If you wanna just chill out and ask questions and be surrounded by people who think they know more than you, and are kind of obnoxious, go check out Tayo. You'll find a lot of people who think they're really smart there, and it's kind of cringe sometimes, but it's also funny because Tayo deals with it expertly, and always has a smile on his face, which I could never do. I would just have no patience for such. Go check that out. Who else? Who else do you want to check out? Tayo's great. Tayo is great. Tayo is awesome. By the way, if you want to participate in trying to solve a problem, I think Tayo has a fun problem that seems unsolved and tractable. You might want to go check that out later. Be a part of that process. What's Project Euler? I don't know what that is. Yeah, I'm very smart crowd. Yeah, exactly. Exactly. But there are some smart people in the chat. It's just that there are also some that are like they say a lot of words, and it becomes apparent to others. Crow is the smartest in that chat. Yeah, Crow is notorious for this. Like, you go there, Crow just starts spamming like, oh, it's just the Theorem cohomology of that, and I really bet that the person doesn't actually know what Theorem cohomology is, like probability wise, because it's very hard to know that, and it's just unlikely. But then you can also figure it out by like future comments where they ask like, what is a vector bundle or something? Like, wait, what? How do you not know one? Yeah, it's great. But Crow is notorious for this. Crow is notorious for this. So, but Tropical is the opposite. Tropical is great. Tropical is open, just eager to learn. Tropical is the only person here that's not a degenerate, because apparently they don't like being called a degenerate, believe it or not. The Tropical is one exception to that rule. Well, actually, yes, Dr. Young's lab. Actually, right, exactly. Fruitcake, let the 5G stay away from you and your family. Let you be protected by from the 5G radiation, Fruitcake. Okay? Crow, sometimes they do. And Tayo is wonderful with that. Because actually it's kind of nice to have, if like a kid comes in and just sort of asks an algebra question, like I have a group, it's acting on a set, that kind of algebra. And then Tayo just wonderfully explains it. And then you'll find someone in the chat who'll be like, oh, it's just blah, 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 big words, blah. Tayo, your explanations are so long and unnecessarily this and conceptual. Yeah, that's what makes him good. That's the sign of a true mathematician. They can explain things simply down all the way to the fundamentals without big words. Like automorphism class. That's what you learned today. Automorphisms. Okay. Get out of here. Let's get out of here. I'm not gonna raid. Is there anyone? Let's see. I just hate the process of raiding. Okay, who's out there? Professor Peter's out. I don't know. Dr. Young's lab, can you just start your stream real fast? I can raid it. Dump these degenerates in there. Oh, no Professor Peter. Alright, you know what? I'm just gonna create an emergency. And we'll create an excuse to get out of here, okay? Alright. Wait, what is that? Wait, hold on. Let me change this. Hold on, just a second. There's an earthquake. Oh my god. You seeing this? Music is inappropriate, is not sufficiently. Wow. Folks, I really gotta go. I really gotta get going, alright? So it was great knowing you. Practice conjugating random elements by other random elements in your favorite group. I'll see you in office hours at 5 today. Or in a calculus in about an hour where I have to make up an... It's 10:50. Okay, big earthquake. Okay, I gotta get out of here. See you, folks.